In episode 16, titled DNS Resolution Flow, Dependencies, Recursion, and Where Failures Hide, we treat name resolution as a chain you can walk aloud, because most domain name system failures become easy to reason about once you picture the steps in order. The exam loves this topic because it hides behind symptoms that look like application outages, network outages, or random slowness, yet the root cause is often just a broken link in the resolution chain. When you can narrate the chain from client to final answer, you stop guessing and start isolating where the break must be. That narration mindset also helps you avoid trap answers that fix the wrong layer, because name resolution depends on both correct configuration and basic network reachability. Domain name system is not one box. It is a distributed service that relies on recursion, caching, and authoritative ownership, which means failures can hide in multiple places. The objective is to make your mental model so clear that you can diagnose a hostname failure without needing a console or a diagram. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. The chain begins with the stub resolver, which is the client-side component that sends queries to a recursive resolver rather than attempting to traverse the Internet's naming hierarchy itself. The stub resolver is typically part of the operating system or application runtime, and it is responsible for deciding which resolver to ask, how to handle timeouts, and how to interpret responses like "no such domain." It usually learns the address of the recursive resolver through configuration delivered by Dynamic Host Configuration Protocol or by local settings, and that means it is already dependent on foundational network configuration being correct. The stub resolver's job is to ask a question like, "What is the address for this name?" and to pass the answer to the application in a usable form. If the stub resolver cannot reach its configured recursive resolver, the client may behave as if the application is down, even when the target service is healthy. In exam scenarios, when one device fails while another succeeds on the same network, client resolver configuration and stub behavior are often part of the explanation. The recursive resolver is the next link, and it is the component that does the heavy lifting by contacting other domain name system servers to find an authoritative answer. Recursion means the resolver takes responsibility for walking the hierarchy on the client's behalf, rather than simply returning a referral and expecting the client to continue. The recursive resolver may be a corporate resolver, an internet service provider resolver, a cloud-managed resolver, or another trusted service. And its reliability matters because many clients depend on it simultaneously. It applies caching, respects time-to-live values, and handles retries, which is why it can dramatically improve performance and reduce load on authoritative infrastructure. If the recursive resolver is misconfigured, overloaded, blocked, or returning bad cached results, many clients can be affected at once, producing broad yet confusing outages. In exam logic, scenarios that describe "everything is slow" or "many services are unreachable by name" often point toward recursive resolver issues rather than toward failures at the application itself. When recursion is needed, the recursive resolver contacts the root, then the top-level domain servers, and then the authoritative servers that own the zone for the name, and that hierarchy is the backbone of public name resolution. The root servers do not know the answer to most names, but they know where to find the servers for each top-level domain, such as the servers responsible for a suffix like .com. The top-level domain servers similarly provide referrals to the authoritative servers for the specific domain, and those authoritative servers provide the definitive records for names within that domain. This referral chain is why name resolution can continue even when individual servers change, because ownership and delegation are part of the architecture. In practical terms, if the recursive resolver can reach the Internet naming infrastructure, it can usually find the authoritative sources unless delegation is broken. In exam scenarios, delegation issues are often hinted at through consistent failures for one domain while other domains resolve normally. The important point is that recursion is a journey through referrals, and every step depends on reachability and correctness. Caching is where domain name system becomes fast and where changes become tricky, and time-to-live values are the control knobs that determine both speed and change propagation. When a recursive resolver caches an answer, subsequent clients get responses quickly without repeating the full recursion process, which reduces latency and load. The time to live tells the resolver how long it can keep that cached answer before it must ask again, which is why time to live directly influences how quickly a change becomes visible. Longer time to live values improve performance and reduce query volume, but they also slow down corrections when an address changes, which can extend an outage window after a migration. Shorter time-to-live values allow faster change propagation, but they increase query volume and reliance on resolver reachability and capacity. In exam terms, if a scenario includes a recent change and some users still see old behavior, time-to-live and caching are likely involved. Understanding caching helps you interpret why a fix in the authoritative zone does not always produce immediate improvement for every client. Split horizon resolution introduces another layer of complexity because answers can differ based on client location or the resolver that receives the query. In split horizon designs, internal clients may receive internal addresses for a name, while external clients receive public addresses, allowing the same name to be used for both internal and external access. This can be useful in hybrid environments, but it also creates failure modes where one population works and another fails depending on which view they receive. The behavior is often driven by which recursive resolver the client uses, which network it is on, or which policies apply to its queries. If internal clients accidentally use an external resolver, they may get public answers that route poorly internally, causing latency or failure. If external clients accidentally receive internal answers, they may see unreachable private addresses, causing clear failure. Exam scenarios often hint at split horizon issues by describing location-dependent success, such as works on the corporate network but fails on virtual private network, or the reverse. The right answer typically involves aligning resolver selection and views with intended client location. Name resolution also depends on basic network reachability and correct default gateway behavior, which is why domain name system issues can be caused by what looks like a routing or segmentation problem. The client must be able to reach the recursive resolver, and the recursive resolver must be able to reach the authoritative infrastructure. And both of those are network paths subject to policy and routing constraints. A wrong default gateway can make a client appear partially connected, such as being able to reach local devices but not the resolver, which produces name failures that seem mysterious to users. A firewall change can block domain name system traffic to the resolver, or block the resolver's outbound queries, producing broad name failures that look like internet outages. In hybrid environments, routing asymmetry can cause queries to leave but responses to be blocked on return, which looks like timeouts rather than explicit errors. The exam often tests whether you remember that domain name system is not magical and still depends on reachability, so a correct design includes both resolver placement and network policy that supports it. This is also why "the server is up" does not guarantee the name will resolve to it, because the path and the resolver must both work. To make the chain concrete, walk a packet from a client query to the final answer, because this narration reveals where failures can hide even when the overall system seems healthy. A client application asks the stub resolver for a name, and the stub sends a query to the configured recursive resolver on the network. If the recursive resolver has a cached answer within time to live, it responds immediately with the record, and the client proceeds to connect to the returned address. If it does not have a cached answer, the resolver queries the root servers to learn the top-level domain delegation, then queries the top-level domain servers to learn the authoritative servers for the domain, and then queries those authoritative servers for the specific record. The resolver receives the authoritative response, caches it according to time to live, and returns it to the client, which then initiates its actual application connection to the resolved address. This walkthrough shows that a name resolution failure can occur at the client, at the recursive resolver, in the resolver's outbound reachability, in delegation, or in authoritative data, and each point produces different symptoms. On the exam, the ability to place the failure in the chain is more valuable than memorizing obscure record types. Common failures have recognizable signatures, and you should be able to associate errors like no such domain, server failure, timeout, and stale cache behavior with likely points in the chain. A response indicating no such domain often means the authoritative side says the name does not exist, which could be a genuine missing record or a mistyped name, but it can also be caused by querying the wrong view in split horizon designs. A server failure response often means the resolver encountered an error during recursion, such as unreachable authoritative servers, misconfigured zones, or internal resolver issues, and it can feel intermittent if the resolver is struggling under load. A timeout often indicates reachability or policy problems, because queries leave but responses never return, or the resolver cannot reach the upstream servers needed to complete recursion. Stale cache behavior appears when clients continue to receive old answers after a change, often because time to live has not expired, or because caches exist in multiple layers, including client-side caches. In exam scenarios, recognizing these patterns helps you choose answers that address the correct link, such as fixing delegation, correcting resolver configuration, or flushing or waiting out caches rather than rebuilding applications. The key is that domain name system failures are rarely random. They are often consistent with the type of response observed. Wrong domain name system server configuration can cause broad but confusing outages because clients may appear connected while failing to reach many services by name. If clients are pointed to a resolver that is unreachable, they will time out on name lookups even though direct Internet Protocol connectivity might work for known addresses. If clients are pointed to a resolver that responds but lacks the necessary views or forwarding rules, they may receive wrong answers or no answers for internal names, causing internal services to appear down. If clients are pointed to an external resolver from inside a split horizon environment, they may receive public addresses that route through inefficient paths or that fail due to internal policy, causing slow apps and inconsistent behavior. These failures are confusing because some services might still work, especially those accessed by cached answers or by hard-coded addresses, making the outage feel partial and random. On the exam, if the scenario mentions widespread issues after a network configuration change or a new site deployment, wrong resolver assignment delivered through dynamic host configuration protocol is a strong candidate. The best answer often focuses on fixing resolver configuration and reachability before touching application servers. A common pitfall is assuming that Internet Protocol connectivity proves name resolution works, because being able to reach an address does not mean you can reach the name that points to it. You might be able to ping a server by its Internet Protocol address and still fail to connect by hostname if domain name system resolution is broken or returns a different address. This pitfall leads teams to conclude the network is fine, and then they chase application settings, while the real failure is simply that clients cannot translate names into the correct addresses. Connectivity tests also sometimes use cached answers, which can give a false sense of success even while new clients or new names fail. In hybrid environments, some traffic may route correctly while domain name system queries are blocked, which makes the experience even more confusing. The exam tests this by presenting scenarios where connectivity appears available but services fail by name, and the best answer focuses on the resolution chain rather than on basic reachability alone. The takeaway is that name resolution is a separate dependency that must be validated, not assumed. Another pitfall is cached bad records persisting after fixes, because caches exist at multiple levels and time-to-live values control how long incorrect answers live. When an incorrect record is published and then corrected, recursive resolvers that cached the bad answer may continue to serve it until it expires, and clients may do the same in their local caches. This produces the classic "it works for me, but not for you" pattern, because different clients may query different resolvers or have cached different answers at different times. Caches are also why rapid back-and-forth changes can be dangerous, because you can create a mixed population of cached values that takes time to converge. In scenario questions, if a change was made recently and behavior differs by user or location, caching and time to live should be considered as root causes of the inconsistency. The correct response is often to respect time-to-live planning before changes and, after a mistake, to recognize that convergence takes time or requires targeted cache management. The exam may not ask you to flush caches explicitly, but it often expects you to understand why a fix is not instantly universal. A memory anchor that keeps the chain straight is client, recursive, root, top-level domain, authoritative, cache, because that sequence matches the practical path an uncached query takes. The client begins with the stub resolver, which hands the question to the recursive resolver that the client trusts. The recursive resolver consults cache first, and if it lacks an answer, it traverses root, top-level domain, and authoritative servers to obtain the record. The cache then stores the result under the time to live, so future queries are fast and consistent until expiry. This anchor is useful because it also maps to where failures hide, since each element can be unreachable, misconfigured, or returning unexpected data. When you can recite the anchor, you can place the symptom in the chain quickly, which speeds up elimination of wrong answers in scenario questions. The exam rewards this kind of structured thinking because it mirrors how real responders isolate name issues under pressure. To end the core with a diagnostic prompt, imagine an application failing when connecting by hostname, but succeeding when connecting by Internet Protocol address, and decide what that implies before you chase the application. This pattern strongly suggests a name resolution issue, such as the client using the wrong recursive resolver, receiving the wrong answer due to split horizon view mismatch, or receiving no answer due to resolver reachability failure. It can also suggest stale cache if the hostname resolves to an old address that no longer serves the application, while the correct address works when used directly. If the failure is limited to one network location, suspect resolver assignment or split horizon behavior, whereas if it is widespread, suspect a recursive resolver outage or authoritative data problem. The key is that the application is likely fine if it works by address, and the failure lies in translating the name to the correct destination reliably. In exam terms, the best answer usually focuses on confirming resolver configuration, reachability to the resolver, and correctness of domain name system records rather than on tuning transport or rewriting the application. When you train yourself to interpret this prompt pattern, you will avoid wasting time on the wrong layer. In the conclusion of episode 16, titled DNS Resolution Flow, Dependencies, Recursion, and Where Failures Hide, the main takeaway is that name resolution is a chain, and every link in the chain can fail in a distinct way. The stub resolver asks a recursive resolver. The recursive resolver uses cache and, when needed, traverses root, top-level domain, and authoritative servers to obtain a definitive answer. Caching and time-to-live values control both speed and change propagation, and split horizon designs can produce different answers by client location, creating confusing location-dependent failures. Resolution depends on network reachability and correct default gateway behavior, and common failures include no such domain responses, server failure responses, timeouts, and stale cache effects that linger after fixes. You avoid pitfalls like assuming connectivity proves name resolution and forgetting that cached bad records can persist, causing inconsistent experiences across clients. Assign yourself one resolution walk practice by choosing a service you use daily and narrating the chain from client to recursive to authoritative and back, including where caching could hide an old answer, because that narration is the skill that turns domain name system from mystery into method. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.